Uh, we've been talking about derivatives. I think today maybe the last of our times to talk about derivatives, specifically using derivatives to show that a language is not regular. Maybe we'll just do a simple example, and then I want to do some more interesting, I suppose, harder examples. So derivatives for non-regular languages. How about like that? Look at those sloppy curly brackets. I was just reading a math tweet today. Not a tweet. I use Blue Sky, which is like a Twitter clone. It's the same as Twitter, but for people who don't like Elon Musk. And they, one of my friends posted, I think yesterday, about how satisfying it is to be teaching a class and draw perfect curly brackets. Not that this happens often, but every so often it looks great. These ones don't look great. Can be satisfying. Anyway, this one is not regular. That's what we would like to demonstrate. All right. Generally, sort of to kind of get a feel for these, if you ask me on a casual level, what is it about this language which makes it not regular? I would say it is the repetition of this exponent, the same exponent, the n, 3 times. Can you believe it? With c's in there. Even if there were only 2 of them, a to the n, b to the n, that's not regular. And it's because of the repeated exponent kind of messes up the language in a way which makes it impossible to be regular. But anyway, here is how we do such arguments. You have to write a little proof, but actually almost all of the proof is totally formulaic. It's just you have to say a few specific things. So I'm going to begin by saying let. The idea, if you recall, is that a regular language can only have finitely many different derivatives. That's because every derivative corresponds to moving the starting state to a different spot. And if it's regular, then there's only finitely many spots you could move it to. And so there are only finitely many different derivatives. So your goal to show something is not regular is to somehow determine a way to take infinitely many different derivatives. And in this case, and this is just something that you will learn to get a feel for, you kind of look at the beginning and you take derivatives which will cancel off various pieces of the beginning of these strings. So in this example, I want to do derivative with respect to a to the I. All of these strings in here start with a bunch of a's, and I'm going to cancel some of them, where I can be any number. So I could be 0, 1, or 2, and these, each one, they'd be different, but like the D1 will be the ones where you cancel one of the a's. D2 will be the ones where you cancel 2 of the a's, and so on. So I'm going to call this di is this derivative of L, and what would that look like when you write it as a language? That's a nice looking bracket right there. Not perfect, but pretty good. It looks like this, right? That's the format of these derivatives. A to the n minus I, b to the n, c to the n. And all you got to say is those sets are all different from one another. For various i's, like for instance, if I equals 1, this means you have like 1 less a than these guys. If I is 2, you have 2 less a's, and so on. And that's different. It's different to have 1 less a versus 2 less a's. So I will just say these are all different. For various I. So that means L is not regular, because we have infinitely many different derivatives. That's that. So L is not a regular language. All right. So it is, like I said before, you have to write a little proof, but basically you're always going to end with that sentence. The creativity really just comes right in here. You have to decide how to choose the appropriate derivatives to make, and the goal is you want to make it so that this answer is different for each different value of I, or at least you get infinitely many different answers. All right, let's just try another one, another sort of simple one, and then we will do some that are a little bit more interesting. How about BA to the N followed by ab to the n. All right, we should be able to play the same trick. Again, what sort of on a very basic level, to me, what makes it not regular is the fact that I have a repeated exponent of n there. All right, how are we going to write this out? I would say it's always going to be like this. We have to decide what. Anybody have a suggestion? What can I use for the derivative? Yeah. BA, I agree. BA to the power I, right? You want to cancel off part of the beginning of these strings. That's the idea. BA to the power I. Remember, BA to the power I is different, of course, from B to the I to A to the I. And it would not be correct to do derivative with respect to, say, just B to the I or something like that. Anyway, what is this as a set? Sorry, I should put L. It's the derivative of L, right? And what is that? It is, how I would write that, it would be AB to the n minus I. Sorry, BA to the n minus I followed by AB to the n, like that. And again, these are all different for different i's because, for example, I equals 1 means there's one less BA than there are of the ABs after it. I equals 2, there's 2 less, and so on. I know I should be using the word fewer rather than less, but I can't be tamed sometimes. All right, so anyway, these are all different. So L is not regular. That's the idea. All right. Any thoughts about these ones? So these two, I would say, are easy ones. Like it's very straightforward. Once you know what you're doing, it's not hard to look at this this formula for the format of this string and decide what the derivative you should do ought to look like. All right. Let's just try one more that's still in the various, or in the same general idea. How about for L equals, maybe for this one I won't write out the whole proof. We'd use any ideas here? I want to use, let's decide what derivative to use here. I want to, again, cancel off the beginning of the string. Yeah? AB to the I. Yeah, great. So this one is only slightly different, and it's AB to the I, like that. Excellent. Yeah. In order, remember, the sort of the thing that you want to play around with is these n's, right? The repeated n. And in order to cancel off some of these b's, you have to first cancel this a at the beginning. So I cancel, when I'm doing this derivative, it cancels one a and then some of the b's. And so this one will look like b to the n minus I, a to the n, right? That first a has been canceled out because I did the derivative starting with a first. All right. This is how we do it. Okay, let's try one that's a little trickier, I guess, a little fancier. How about this? A to the m, b to the n, a to the n. All right. Sorry, I'm a little distracted by the Oval Office over there.
Can you close the door?
It is closed. Yeah.
Oh, is that through that class?
I think it's just through that door right there. Yeah. Should I tell them to turn it down? I don't think I know that professor in there. Doesn't sound like math, so I don't know them well. Okay, this language. What's weird about this one is, and this may be a problem for us, like before, I want to use the fact that here's this repeated n, and so I'm going to try to cancel some but not all of the b's. The problem is they're sort of like protected by this a to the m, all right? And we'll have to think a little bit about that. Here's one basic idea that would occur to anybody. Don't write this down because this is actually not correct. Something like that. the derivative with respect to a to the m, b to the I. The idea here is this will first cancel all of these a's, followed by some of the b's, which is exactly what I want to do. Can anyone say what's the problem with that? This actually is not really allowed to do this. A to the m, b to the I here. It is more or less exactly what we did here, right? I had one a, and so I put a here. Yeah?
Is it because you don't know how many A's are going to be in there? Like M and I can be different M's.
Yeah. M can be any number. So when you say just do this derivative, a to the m, my reaction is, what is m? And the answer is like, oh, m could be anything. Well, then you're not actually talking about anything specific when you say this, right? So this is actually bogus because that right there is not a specific number, right? That could be anything. And so when you say this derivative, I mean, maybe you mean something like you just do those derivatives for all possible m, but then that's not an ordinary kind of derivative anymore. So this is because m is not a specific number. So we cannot use m in your little formula when I take the derivative. Anybody have a weird, so the resolution to this is pretty weird. Anybody have an idea that we could do? Somewhat outside the box. Got an idea? b to the I. Yeah, this is what we're going to do. I think you got some splaining to do. Derivative, just b to the I. No a's at all. My initial reaction to this would be, that's not going to work because you get these a's here, and you're just going to get, like, this means if these strings begin with b's, you cancel those b's, but if they don't, you just throw them away entirely. You get the empty set. How do you respond, young man?
No.
Is this a real problem?
No, because if it starts with, you're getting rid of the a's anyway, so every string will be e to the n minus I, a to the n. So even if it starts with an a, you're getting rid of it.
Mm-hmm.
But it would have given you, even if you did your bogus thing, it would have given you the same set as if you got rid of all the a's.
Mm-hmm. So I think what I heard that I like was, if it started with an A, then you would just ignore that string entirely, and it would not be part of your answer at all. But some of these strings actually use m equals 0, and so some of these strings don't begin with A. And those strings will be left over when you do this derivative. All right, so the answer, I think this is what he meant, will indeed be b to the n minus I, a to the n. And the reason that that's the answer is because only those strings with m equals 0 exist, or I will say something like survive in the derivative. Right? In the original language L, most of the strings actually begin with A's, but not all of them. Some of them just start with B's. Those are the only ones which will appear in the answer of the derivative, and that's why the answer is like this. Rather than the empty set, I think it's tempting to look at this and say the derivatives with respect to B will just be the empty set because these strings all begin with A. But the fact is they don't all begin with A. Some of them use m equals 0, and so those ones give us this as the answer. Strange but true. But anyway, those are now all different, right? These are all different. These are all different. So L is non-regular. All right? These are the somewhat weird things you have to do sometimes. All right. Any thoughts about that one? I got a few more of the same somewhat weird type. And then I have some for you all to try. How about this one. All strings x such that the number of a's in x is equal to the number of b's in x. So x has the same number of a's as b's in it. All right? This is another example where, so in this case, actually, you have no formula to use for x at all. And this is a bit troubling because I like to see a formula with n's in it, and then I change it to something like with n minus I in it or something like that. But you can't do anything like that in this case because this is just all strings x where the number of a's is the same as the number of b's. But in fact, you can, and like, you don't even know what the x starts with. Does it start with an A or does it start with a B? We don't know. But we can still use the derivative. Actually, you can do this either way. I'll just do A to the I, but B to the I would work just as well. Here again, we have a scenario where actually we don't know that these strings begin with a bunch of A's. And in fact, most of them don't. But some of them do. And those are the ones that are going to appear as part of the answer here. So when I'm doing this derivative, we can assume that the strings I'm talking about are ones with began with I, different ones of them. All right? And of those ones, when I cancel off those A's, can anybody say what the set would look like afterwards? So I'm going to write this again like all x such that, but it's different this time. Now we are considering only those strings which happened to begin with a bunch of A's and then canceling those A's off. Can you say, how would you describe what remains? Yeah?
More B's than A's?
More B's than A's, yeah. Can you say how many more in particular? Actually, you can be a little more specific. Think about how many A's got canceled here. I think I of them. Yeah, it sounds funny when you say it, but it's something like there are I more B's than A's. Or the number of A's, maybe I'll say it this way, something like the number of A's equals the number of B's minus I. I think I said that the right way around. There are less A's now, right? How many less? I less, because we canceled I of them. So the number of A's in X is now the number of B's minus I. And of course, the punchline of the proof still works here. These sets are all different for various different I's. For I equals 0, they are equal. For I equals 1, there's 1 less. For I equals 2, there's 2 less, etc. All right? These are all different. And so L is not a regular language. These can be a little tricky to think through sometimes. How about, can I just say same for something like, on the general theme of like repeated exponents, of course you don't see repeated exponents here, but I still see some kind of matching number of this and this. And this is what, to me, is like the hallmark of a language which is not regular, is some kind of a matching amount of these guys and these guys. That, in general, that is not allowed for regular languages. And here's another, this is a little less clear. It's not really about a matching amount, but this is also non-regular. How about the number of A's is less than the number of B's? All right? This also is not a regular language. And you can use the same derivative in this case. So here, the derivative that you want to take would be something like a to the I. And then this ends up saying the number of A's is less than the number of B's minus I. And again, those sets are all different from one another. We started with just the number of A's is less than the number of B's. But if you're using, say, I equals 1, it means the number of A's is less than the number of B's minus 1. Or I equals 2 would say the number of A's is less than the number of B's minus 2. And those are different sets from one another. It means somehow like there's a lot less A's, not just less, but less, even more than 1 less, or more than 2 less, or more than 3 less, and so on. All right. So sometimes you have to do somewhat weird variations. I have 2 more examples, and then I have some for you all to try. Maybe I've been writing these a little informally. I'm going to try to write real proofs from now on. How about this? X squared. X is in AB star. X squared, yes?
So for all comparisons on like the X language, or not language, but like the X,
Yeah.
it'll automatically be not regular.
For all comparisons, I would say generally speaking that's true. I don't know about all. Like you could say some kind of stupid thing like the number of A's is less than, I don't know. If you said like the number of A's is less than or equal to the number of A's or something, this surely is not what you mean. But generally speaking, if you are saying things about, say, the number of A's versus the number of B's, most non-stupid things that you want to say will make it into a non-regular language. Yeah. All right, how about this? X squared. This is kind of a weird language. I don't know if we've talked about this before, but this is all strings which look like something squared. This would include something like, A, B, B, A, B, B, A. So like ABBA is in this. Or just, it's any string where you could break it down into 2 parts which are equal to one another. That's what it means to be a something squared, right? Again, this is an example where we don't actually have a formula for what x squared looks like. Like we don't know if it starts with an A or a B or whatever, but we're just going to take derivatives with respect to A, and that will mean that we can assume that it starts with an A. So we will do, let's consider something like derivative with respect to A to the I of this language L equals, maybe I'll do a little sort of work on the side here to try and figure this out. So when you take this derivative with respect to A to the I, it means you are assuming up front that x squared begins with A to the I. All right, so we can assume that x squared starts with A to the I, right? And I think what that means as far as like what this string looks like, what does it look like overall if it starts with A to the I? So that means I think we can say x squared looks something like A to the I followed by something else, y, and then times A to the I, y again. Because it has to be the square of something. And if that something starts with a bunch of A's, then the rest of it has to look like that, right? This is what it looks like if you have a square of something that also starts with a bunch of A's. And then now I think it's clear what happens when you take the derivative of that string with respect to A to the I, right? The first A to the I gets canceled off, and then the rest of it remains. So this is weird, but it is a fact. The derivative with respect to A to the I of L is equal to all strings of this type, y A to the I, y, where y is in AB star. Right? It's because these strings originally, in order to be squares of something, they must have, in order to be squares of something and they started with A to the I, then that means they look like A to the IY followed by A to the IY. And then I'm canceling, when I take the derivative, we cancel the A to the I at the beginning, and all that remains is this. Yay. All right? And are these all different for various i's? Yes, they are. Like when I equals 1, this means a string which has one A in the middle, and then the same thing on either side. And if I is 2, that means 2 A's in the middle, and the same thing on either side. And these are all different sets from one another. All right? So if I were to write the real proof here, maybe I'll just, all of that was kind of like work on the side here, but the real proof would look something like let di be derivative with respect to A to the I of L, which is, like I said, y A to the I y, such that y is in AB star. This is the weird step that you ought to be skeptical of if somebody just said that out of nowhere. But anyway, These are all different. So L is not regular. Right. Any thoughts about that one? This is a somewhat strange example. All right, let's try one more. This is just a little variation of that. How about the language is X, XR. Again, X is in AB star. This is something we haven't really talked much about, but XR means the reverse of X. It's just whatever X is as a string, you read the same thing in the reverse order. So X followed by X reverse. It means this is basically like a palindrome type string. It has the first half, and then the second half of the string is exactly the same as the first half, but read in the opposite order. All right. This also is not regular. And we are going to do something very similar to what you can still see up here, right? I'm just going to, there's no formula here, so I'm just going to do derivatives with respect to A, just because I have nothing else, no reason to do any other derivatives, but I'm going to do derivative with respect to A to the I. We'll have to think about what is this going to look like then when I take that derivative. So this is not my proof so far, but we are, in order to do this, I'm going to assume that X looks like A to the I Y, right? Because I intend to take the derivative with respect to A to the I, that means we might as well assume that X begins with A to the I. So what does the entire string X, XR look like? Someone want to say? What is X followed by X reverse? I'm trying to follow the same steps that we did in the previous example. Before I had X squared, right? And X squared looked like that. What do you think?
It'll look like AI to the Y, Y,
AI, Y, AI. A to the I, Y. What do you say? Y, A to the I, right?
Yeah.
Yes. I'm almost, I almost agree. Anybody have a slight suggestion? Just one little thing. This is a little tricky, but X followed by X to the R. For example, if X is A, B, A, something like that. So this is like A squared, and then Y here. This is X. X to the R is the reverse of that, A, B, A. So here I see A squared. That's not quite Y, though. What is it? How can we write that? Yeah?
Can you put like reverse around?
Reverse. I think actually all we need is this is Y reversed. And then followed by the AI at the end. Yeah, this is the reverse of Y, not just Y. So it's like that, right? X followed by X reversed is A to the IY, because that's what X is. And then the reverse of that would be Y reverse followed by A to the I. You gotta reverse the Y. Reverse the reverse. Right? It's like in Uno. Sometimes I play with people. You can put a draw two on the draw two, right? And I always say, can you reverse the reverse? Then they start getting confused. They say, no, of course not. Idiot, you can't reverse the reverse. Yeah. All right. Okay, anyway, this is what X followed by X to the R is. So that means when I do my derivative with respect to A to the I of L, the format of what remains, X followed by X to the R looks like this, but I'm taking the derivative and canceling the initial A to the I. And so this set looks like that. Y in AB star. This, in my opinion, you have to really think carefully about this. To go from here to here, this is a weird answer to get starting from there. But You have to think through exactly what this string is going to look like, and then what's left over once I cancel A's off the front of it. All right. But again, these are all different for various different I's, right? Basically, what you see here is Y followed by its own reverse, and then with like one extra A, or two extra A's, or three extra A's at the end. And those are all different from one another. All right. All right. I got some for you all to think about. See if you can show these are not regular. I got 3 here. Banabin. So the last one there, I'm talking about binary strings, that is zeros and ones for the alphabet, and then that X bar just means, I said bar means not. It's like the bar of a 0 is a 1 and the bar of a 1 is a 0. I hope everybody knows what I mean by that. All right, try and write the whole proof. It's not a big deal to write the whole proof in these ones, but see how it goes, and then we can talk about them. Feel free to chat with your friends about it. And then I think we'll talk about something completely different. This one is sort of deceptively simple. I would say if you put n minus I here, then you should just say n minus n. Right? N is less than n. Because that's what it used to be. That's the relationship between n and n. You cancel some things, but that's still, yeah. Still clear? Yeah, but this is right. That's weird. Yeah. Mm-hmm. Yeah, this is confusing. Yeah, it should be understood. I don't know if it's clear, like x equals that. And then x followed by x bar must be that y followed by 0 to the I bar.
But if it's just a the goes on back,
It's kind of like that. Yeah. Okay. Yeah, you just change the zeros to ones, and then you should say y bar. So whatever's in there also needs to get switched. Over here. Sorry, I would say this is what x bar is. If you say x bar, it's a little different. Stuff good here? Yeah, that's great. Could be inspired by the reverse example. Some of that. All right, can we chat about these? I saw as I was going around, pretty much everybody did the first. Well, the first one I would say is a very straightforward one. You should do derivative with respect to b to the I, and it just cancels some of the b's at the beginning. The second one is also fairly straightforward, although kind of confusing how you're going to write the answer of the derivative. I think the simplest way to write the answer is like this. You started with n less than m, and if I just cancel some of the a's, in my opinion, the easiest way to write that is like this. It is now, I canceled off some of the a's, but the original relationship between those two numbers, n and m, is the same as it used to be. Some people, as I was walking around, tried to write, you could also write this equivalently, although this to me is more confusing. You could try to write it like this. I think the appropriate thing is something like that, if you want to write it this way around. But that is, to me, like I said, more confusing than this, although I believe they express the same set either way. And in any case, those sets are different for various i's. To me, it's a little clearer to see that from if you write it this way. What about the last one? That's the perhaps most interesting of these, in my opinion. It is a lot like the x reversed example. The idea is I'm going to, as I walked around, I saw various people did it in different ways, but I'm going to do this derivative with respect to 0 to the I. You can blow your friends' minds if they're in a calculus class. Ask them, what do you get when you take the derivative with respect to 0? Yeah. My answer as a calculus teacher would be, you done messed it up if you took the derivative with respect to 0. You just don't do that. You can do it in this case. Anyway, if I'm doing the derivative with respect to 0 to the I, that means I'm going to consider x to look like that, right? If I'm using this derivative, it means I may consider that x has this format already. And so that means that bar of x will be 1 to the I followed by y bar. All right? Every 0 gets changed to a 1 and vice versa. So the zeros at the beginning become 1s, and then what's in I don't know what it was, but whatever it is, it gets the bar. So that means x bar has this format: 0 to the I, y, 1 to the I, y bar. Right? That's the format of x bar. And so now we can say what our derivative is. So di is going to be this derivative. Now, if you took the derivative with respect to 1, that's just as good. Everything would be, slightly different. This is now going to have this format: y 1 to the I y bar, where y is anything in 0, 1 star. And those are all different. They have just some certain number of 1s in the middle. And if I choose different i's, it'll be different numbers of 1s in the middle. All right, any thoughts about that one? I think everybody said something like that. All right, excellent. This, I think, is all I wanted to say about regular languages. About non-regular languages, right? Showing that a language is not regular. You use derivatives in this way. Any thoughts? All right. Let's maybe we got some time. We can start talking about the next big whoop. Our next sort of big topic is yet another way to generate languages with something like a machine. And this one is really new, so you can make languages which are not regular using these types of things. I am referring to grammars. All right, grammars. All right. Grammars are used to define languages. So a grammar defines a language. And they work kind of like grammar in real life. Sort of the idea of a grammar in real life is that there are certain rules about how you build a legal sentence, say in the English language. Now, it's debatable how real those rules are. Like in real life, when people speak, they don't always use so-called correct grammar. And really, if you try to nail it down, there is no such thing as correct rules for grammar versus incorrect grammar. It's just like people talk in various ways. But anyway, we're gonna imagine that a language can be defined according to sort of rules about how you assemble strings in that language. So here is an example. Maybe I'll just do sort of a cute example. These are sometimes called formal grammars. For, I'll say something like, it's coming back, baby English sentences. Like, I'm talking about very simple sentences like, I love mom, or you want candy, or we see candy. Right? This is a very sort of rigid type of structure here. If I were describing this in sort of traditional grammatical terms, I would say these are all sentences which have the form sort of noun, verb, object, something like that, right? So the way that you would write this in terms of a grammar, as a grammar, well, I'll write it down first, and then we can talk about what it all means. S, and then this arrow, NVO, and then I'll say N, and then this arrow, I, U, we. So those bars are like a vertical bar. It's a bar. I don't know what I was trying to say there. V, this represents the verbs. Apparently the sort of allowable verbs in these examples are love, want, see, and then O represents the objects, which in this case are mom or candy, right? Sorry, I'm blinking a lot here. All right, this is a formal grammar, and just sort of the ingredients here, we say that S is the starting symbol, and then the arrows describe substitutions that you can make. So the arrows, and actually the name for those, we don't call them transitions in a grammar. The arrows are the derivations, and they are describing substitutions of like little pieces of sentences. Substitutions. All right. And we can write for a given like real life sentence, like up there it says, I love mom, right? Or I want candy. So we can, this is called derive, something like, I want candy. Like so. You would start with, so every derivation must begin with the starting symbol. And then you do a sequence of finitely many substitutions according to the derivations that are specified in the grammar. And this is a weird technicality if you look in our book. S, the arrow, of course, S becomes NVO. That's what this means. You will notice this arrow has kind of like two bars in it. This only has one. I'm trying to match the style of the book. So in the book, I don't really care much about this, but in the book when they write a grammar, they use this arrow here. But when doing specific derivations of specific examples, they use this arrow here. Not a big deal. Anyway, S becomes NVO, and then each of the N, the V, the O, they can become their own thing. And the bars up here represent or. So this line means the N can turn into a I or a you or a we. Right? So here, maybe I'll write that up there. The bar here means or. All right? So if I want to specifically derive I want candy, I have to start with S. I turn it into NVO. Then the N becomes I. So this becomes I, VO. And then I'm going to make the V turn into want, O. And then the O turns into candy. So it finally says, I want candy. All right. I suppose I shouldn't put the period. This is how we use a formal grammar to create strings. All right. Just a little simple terminology here. S, N, V. S is called the starting symbol. These are called non-terminal symbols. Non-terminal refers to the fact that they need to get substituted before you end up with your answer. Like N, V, the O, they are not meant to end up at the end. You're not supposed to see them at the end. That's why it's called non-terminal. Terminal meaning like at the end. These are non-terminal symbols. That's because they don't appear at the end. If you still see them, it means you're not done with the derivation yet. You have to keep on substituting. The other ones, the others, meaning things like I, mom, etc. These are terminal symbols. So a derivation always involves starting with S and then doing a bunch of substitutions until it's all terminals. And then you have your final string. Yeah?
Do you make up letters for N, V, and O every time? Or is it just like that's what they say?
Yeah.
Okay.
Yeah. So I called them NVO because N for noun, V for verb. But yeah, generally, so in our like abstract examples, we're going to use A's and B's for the terminals because those are the things that you try to get to at the end. And then the other ones we'll use like S, T, U, capital, things like that. Yeah. All right, great. You'll see actually these grammars are similar to NFAs or DFAs, but they can create more things, not only regular languages. So we'll see next time. Let me know if you got homework questions.